Hello, I have made a small attempt to make a pendulum clock which is independent of the variation of gravity. Of course, nowadays there are several atomic clocks with extremely accurate time readings. Anyway, this is of a theoretical importance just to show that we can make one such pendulum using very simple things like a helical spring arrangement. So, in my small effort, I have explained in this video also the draft paper which I have uploaded in detail how it works and how to construct it. Now I am going to explain gravity independent pendulum clock. See, we know that the pendulum is governed by the famous equation which I am going to zoom and show it to you now, is 2 pi t equals 2 pi square root of L by G, where t is the time of oscillation of the pendulum from one end to the other end and back to the same end, that is t. Time in seconds. 2 pi is of course a constant. L in meters. G is the gravity at that particular place where it is expressed in meters per second squared. L is the effective length from the fulcrum to the center of mass of the pendulum. So this particular equation is a well-known equation, and we also know that the time period now varies because of these two factors, that is L and G. Suppose if you make L as a constant, then it varies mainly due to the acceleration due to gravity G. We also know that the acceleration due to gravity varies from place to place on Earth itself. Mount Nevado is having the least acceleration of 9.7639 meters per second square, and at the Arctic Ocean surface it is 9.8337 meters per second square. This variation will lead to the time variation. T on the mount by T on the ocean is 1.003568. This amounts to 5.14 minutes in a period of 24 hours. Now, what I am going to tell you is that the gravity on the surface of the moon is 1.62 meters per second square, and when we take the same pendulum clock, T moon by T earth is equal to 2.438. Remember, this is a very huge difference. Time period of oscillation on the moon is 2.438 times that of the earth. It takes a longer time. So that means it creates a huge difference. And similarly, if you take the same pendulum clock to Jupiter, of course it is a gaseous planet anyway, the gravity is 24.79 meter per second square, and look at this, T Jupiter by T Earth is equal to 0.629. That means for every second on Earth, Jupiter shows only 0.629 seconds. Of course, now we want to make the clock independent of the variation in gravity. Even though it works because of gravity only, we will try to make it independent of the gravity, and the logic is extremely simple. Suppose we can make length L, equivalent length L is equal to some constant K times that of the gravity. Then we have that equation T equals 2 pi root K into G by G, where G and G cancels out, resulting T equals 2 pi root K. We know that 2 and pi are constants. Root K is constant for a particular spring. That means we are using a spring which is having this property of deflection is equal to or proportional to that of the gravity. So a normal helical spring will satisfy this particular condition, but there is some problem of what is called as zero length. When we simply take a spring and make it to constrict, then the zero length problem will come. That means at zero gravity it should have no stretch length at all. Therefore this particular construction I have done. I will explain this construction now. The gravity independent construction pendulum consists of a ring here. So this particular ring is a light metallic one, a cylinder wherein we are having two pivot points so that we can mount it on these two and the pendulum will oscillate. There is a plate here with a hole facilitating only this small slender rod to pass through. The plate is fixed at here and there to this cylinder. The cylinder of course here is full. It is shown here in cut section so that you can understand it better. Now the pendulum is here. This is having a huge mass compared to all these parts. That means all these parts are having negligible weight. Even though the weight is negligible, the spring is of course a very slender one, a long one. The spring is fixed to the rod at this end and it is resting on the plate at this particular end. So when there is no gravitational force, say in space, the center of gravity of this pendulum coincides with the pivot point or suspension point, and therefore effective length is 0. When the effective length is 0, it won't oscillate at all. Now whenever it is brought to the earth's gravity, of course there is one more point here. 1 kg mass is assumed here. That mass of the pendulum is 1 kg. Now when there is a gravity of 9.81, what will happen? The spring length is so adjusted that it deflects through 98.1 millimeters in proportional to the gravitational value of the earth. So that means when there is a deflection like that, equivalent length is so much. When the equivalent length is so much, then we can think of compensating that particular gravitational variation effect. Remember, this deflection need not be 9.81 meters. It should be proportional to g only. It may be very small also, but the gear mechanism will take care of this particular magnitude. Anyway, it should be, the deflection should be proportional to the gravity. Now the oscillation is in y direction, the deflection of the spring is in z direction, and therefore the pendulum will oscillate like this and the deflection is downwards. This will facilitate that this deflection take care of the variation in gravity, and time is of course a constant given by this equation t equals 2 pi root k, where that root k depends upon the spring and its materials, length, etc. Initially we can find it out and put that particular value which will never vary. Time is always constant now, even if you take the clock to moon, Jupiter or anywhere, or even on the surface of the earth where there is a variation in gravity. So this particular construction is having some allowable range of gravity. How can we get a spring exactly equal to 9.81 at that particular gravity? How can it deflect exactly 98.1 mm? What we can get is, we can easily get a 50 centimeter spring length which can have 10 centimeter per kg of stiffness. Very easy to get such a spring from the shop. Take the 10 centimeter per kg and out of 50 centimeters we have to cut down. Remember, we have to reduce the length through 10.5 millimeters. So out of 50 centimeter, which is equal to 500 millimeters, we are cutting 10.5 millimeters or 1.05 centimeters, resulting 490.5 millimeter of this spring in its free length. When we do that, the stiffness of 50, that is 10 centimeter per kg, will reduce to 9.81 centimeter per kg or 98.1 millimeters per kg, and since this is 1 kg under gravity on earth, it stretches automatically to 9.81 millimeters. Similarly, if you take it to the moon, where the gravity is just 1.62 meters per second square, the spring will stretch only to 1.62 centimeters or 16.2 millimeters. Now if you take it to the Jupiter, where the gravity is 24.79, the spring automatically stretches to 247.9 millimeters. Of course, there should be initial sufficient length of the spring, so that even on Jupiter, if you want to take it, it should not completely get compressed, otherwise it won't work. Anyway, the range of variation of gravity, if you design it only for the Earth's purpose, definitely you will need a very compact clock. If you use it for a long range from gravity 1 to gravity 25, then the clock length, that is spring length, will increase.